Assalamu alaikum. Myself Sayyid Fawaz, registration number 20T60 और आज हम लैब 8 परफॉर्म कर रहे हैं जिसमें सबसे पहला टास्क है इसमें हमने इम्पल्स रिस्पॉन्स मैग्नीट्यूड रिस्पॉन्स इसमें हमने प्लॉट करना है फिल्टर का. So the code starts by defining an impulse response H as an array of values. These values represents the response of a filter to an impulse at different time intervals. Next, we create a time vector t using the zero column length h minus 1 expression. This vector represents the time indices corresponding to each element of the impulse response. We then use the stem function to plot the impulse response with the time vector t as the x-axis and impulse response h as the y-axis. Now let's move on to the magnitude response. We define a variable n as 1024 which determines the number of frequency points we'll use to analyze the magnitude response. To calculate the frequency vector f, we use the line space function which generates equally spaced points between 0 and 1 and then we multiply it by pi by 2. This gives us a frequency range from 0 to pi by 2. Next, we utilize the freq z function to calculate the frequency response h of the filter defined by the impulse response h. The frequency z function takes the impulse response h denominator coefficient of 1 since we are only considering the numerator coefficient in this case and the frequency vector f. This function calculates the frequency response at each frequency point and store it in the variable h. Finally, we compute the magnitude of frequency response by taking the absolute value of h using the ABS function. This gives us the magnitude response of the filter. In order to visualize the magnitude response, we create a new figure using the figure function and then we use the plot function to plot the frequency vector f on the x-axis and the magnitude response on the y-axis. उसके बाद हमारा नेक्स्ट टास्क है जिसमें we will be explaining a code that demonstrates how window functions can be applied to filter coefficients to improve the performance of digital filter. Okay. First, we have the filter coefficients defined in an array H. These coefficients represents the impulse response of the digital filter. In this example, we have a 7-tap filter represented by these coefficients. Next, we define the length of our window n as 512. The window length determines the resolution of frequency response plot that will generate later. Moving on, we generate three different windows function: Hamming window, Hanning window, and Blackman window. These windows function are designed to taper the filter coefficients towards the edges, reducing the artifacts introduced by abrupt changes. To apply the windowing, we simply multiply each coefficient in the array H with the corresponding value from the window function. This is done for all three windows functions, resulting in H Hamming, H Henning, and H Blackman. Next, we calculate the frequency vector f using the line space function. This vector represents the normalized frequency from 0 to pi by 2. Using the frequency z function, we calculate the frequency response of each windowed filter H Hamming, H Henning, and H Blackman. The frequency z function returns the complex values that represent the magnitude and phase response of the filter at different frequencies. To visualize the magnitude response, we take the absolute value of the frequency responses, storing them in the magnitude Hamming, magnitude Henning, and magnitude Blackman. Finally, we plot the magnitude responses using the plot function. The x-axis represents the frequency in radians, while the y-axis represents the magnitude of the frequency response. उसके बाद हमारा टास्क 2 है जिसमें हमारे पास सिग्नल गिवन है उनको हमने टाइम और फ्रीक्वेंसी डोमेन में प्लॉट कर रहा है along with their magnitude responses. So in the first section, we define a sampling frequency fs at 800 samples per second. Then we create a time vector t using this index, then which represents time values from 0 to 0.02 seconds with a step of 1 by fs. Next, we generate three sinusoidal signals x1, x2, and x3 with different frequencies using the sine function. These signals have frequencies of 500, 1500, and 1700 Hz respectively. To create the composite signal X, we add up the three sinusoidal signals. This results in a combination of different frequencies. To visualize the signal in the time domain, we plot it using a plot function. Moving on to the second section, we start by calculating the length of the signal x using the length function and store it in the variable n. Next, we create a frequency vector f using the formula this. This vector represents the frequency bins corresponding to DFT of our signal. Now comes the interesting part. We apply the fast Fourier transform to our signal x using the FFT function. This computes the frequency spectrum of our signal. To obtain the magnitude spectrum, we calculate the absolute values of the FFT result using the ABS function and store in the variable magnitude. To visualize the magnitude spectrum, we plot it using the plot function, taking the frequency vector f and the magnitude vector magnitude as inputs. In the final section, we plot the magnitude response of the signal within the limited frequency range. We achieve this by setting the x-axis limits using the xlim function, specifically 0 to fs by 2. This range represents the positive frequencies up to half of the sampling frequency, which is known as Nyquist frequency. Restricting the plot to this range allows us to focus on the meaningful frequencies of our signal. We plot the limited magnitude response using the plot function again and passing the frequency vector f and the magnitude vector magnitude as before. This is the magnitude response. This is the magnitude spectrum, and this is our signal in time domain. उसके बाद हमारा लास्ट टास्क है जिसमें हमने एक हमारे ऑडियो सीक्वेंस गिवन है उस पे हमने हाई और लो पास फिल्टर्स अप्लाई करके रिजल्ट्स अप्लाई ऑब्जर्व करने हैं सो पहले इस कोड के पहले 3 लाइन में हमने बेसिकली जो ऑडियो फाइल है उसको उसका पाथ डिफाइन किया हुआ है और उसमें हमने ऑडियो रेड का फंक्शन लगा के उसको रीड किया उसके बाद हमने दो वेरिएबल्स डिफाइन किए हैं कट ऑफ लो और कट ऑफ हाई which represent the low and high cut off frequency respectively. These values will be used in the code in later in the code to filter the audio. Now we set the variable order to 4 which determines the order of the Butterworth filter depth will be applied. The Butterworth filter is a common type of filter used in signal processing. The next 2 lines use the butter function to design the Butterworth filters. The first line design the low pass filter low with the cutoff frequency cutoff low by fs by 2, where fs by 2 represents the Nyquist frequency. The resulting filter coefficients are stored in B low and A low. Similarly, the second line design the high pass filter with the cutoff frequency cutoff high by fs by 2. The resulting coefficients are stored in B high and A high. Here we use the filter function to apply the design filters to the audio data X. The first line filters the audio data with the low pass filter coefficient resulting in Y low. The second line filters the audio data with the high pass filter coefficient resulting in Y high. Finally, we play the original audio X using the sound function passing in the audio data X and the sample rate Fs. We then pause the execution of the duration of the original audio by using the pause function with the argument length of X by Fs plus 1. After the pause, we play the filtered low pause audio while low using the sound function again. We then pause for the duration of the filter audio by using the pause. Lastly, we play the filtered high pass audio by high using the sound function.